Hi, I'm Justin Less, and I will be presenting on the implementation of self-healing concrete in the construction industry. America, one of the most developed countries with the largest economy in the world, received a D-plus rating of its infrastructure in a 2017 report by the American Society of Civil Engineers. In addition, the Federal Department of Transportation estimated in 2016 that the United States has accrued $836 billion in backlog of unmet capital needs to fix the nation's highways and bridges. I know none of us would tolerate a D plus in one of our classes, so why should we tolerate it when it comes to our infrastructure? The state of our infrastructure is at an all-time low, and in this presentation I will be investigating two concrete alternatives that could potentially bring down that gigantic cost and bump that D plus up to an A. These two alternatives are bioconcrete and superabsorbent polymer concrete. In order to compare those two alternatives to the construction status quo, I first will analyze the use of standard concrete in our world. Concrete is a heterogeneous mixture composed of sand, rock aggregates, water, and cement. Important material properties of concrete include its strength capacity and durability, which are highly affected by the concrete mix design and the cement hydration process. Water reacts with cement in a concrete mix over time in a process called hydration, forming chemical bonds which bind the aggregates and sand together. The main reason concrete is so widely used in construction is because of its unique ability to maintain compressive loads. However, as seen in this diagram, concrete performs horribly under tension. When bending under a downward load like in this picture, the bottom side of a concrete beam will always be in tension. This will inevitably cause concrete to crack and fail. The largest costs of concrete production are cement and labor. According to an industry data survey highlighted in the 2017 President's Report by the National Ready Mix Concrete Association, the average price of concrete was just over $108 per cubic yard. While this price does not account for the costs of labor, formwork, or steel rebar reinforcement, this price could still be compared to other concrete mix designs in which those components are expected to remain the same. The production of cement contributes significantly to global carbon dioxide emissions. The International Energy Agency reported in its 2018 World Energy Outlook that the production of cement, the binding component in a concrete mix, contributes nearly 7% of annual global carbon dioxide emissions. The figure here shows the increase of global cement production over time, with an accelerated increase starting in 1980 up until 2020. The environmental impact of standard concrete poses a serious threat to any efforts being made to reduce carbon dioxide emissions and curb the impact of climate change. The first concrete alternative that I'll analyze is bioconcrete. The idea originated from animals and insects' ability to heal themselves. Hendrik Jonkers, a Dutch microbiologist, and his team at the University of Delft in the Netherlands created a concrete that has the ability to heal itself using living bacteria. Jonkers proposed to mix bacillus bacteria into the concrete during its production. This bacteria will lay dormant until water is absorbed by the concrete when it cracks. This water will dissolve the capsules holding the bacteria and allow the bacteria to germinate and produce calcium carbonate to fill the cracks. The production of bioconcrete is very similar to that of Portland cement concrete. The only difference is the addition of bacteria, suspended particles, during the concrete mixing process. Prior to their addition, the bacteria spores are activated and introduced to supplementary cementitious elements like fly ash. Bioconcrete was released to the open market in Europe, costing about $239 per cubic meter, roughly double the price of Portland cement concrete. It is estimated that the total environmental impact of bioconcrete is about half that of concrete, traditional concrete that is. The graph shown displays the life cycle assessment, or LCA, of bioconcrete compared to traditional concrete. LCA is the investigation and evaluation of the environmental impacts of a product, process, or service. LCA evaluates all stages of the product's life and considers each stage interdependently, meaning that one operation leads to the next. Bioconcrete scored a lower LCA score, mainly due to the possibility of recycling bioconcrete into aggregates to reproduce more bioconcrete, hence forming a closed loop by closing its cycle. In addition, this graph indicates that traditional concrete, shown on the right, is much worse in the areas of ecotoxicity and carcinogens. The second concrete alternative that I'll investigate is superabsorbent polymer concrete, or SAP concrete. Nelly DeBelly, I swear that is her real name, a structural engineer at Ghent University in Belgium, said polymers might have an advantage over bacteria, Having an elastic material filling cracks is beneficial for bridges, which must bend slightly under their dynamic loads. In previous applications, superabsorbent polymers have been utilized for wound healing, disposable contact lenses, and diapers, but DeBelli found a use for them in construction. Unlike bioconcrete, superabsorbent polymers do not actually heal the microcracks. Instead, they utilize polymers' ability to absorb water, swelling up enough to cut off water penetration into the cracks. The healing process is the concrete's autogeneous self-healing ability for closing microcracks using unhydrated cement particles. The SAP will also release water slowly to allow for cement hydration, but not a significant amount to saturate the crack. The figure shows this autogeneous process taking place inside a crack. It starts on the left with calcium deposits being eroded. Then cement particles will fill the new eroded crack and absorb water. They then swell up and fill the crack with new concrete. While this concrete alternative is estimated to be environmentally and economically beneficial, it is still in its infancy of production and lacks testing. The polymer additive is the only addition to the Portland cement concrete. That, along with minimal prep for the polymers, will likely make this product much cheaper than bioconcrete. SAP concrete also increases the concrete's durability through internal healing. Therefore, less concrete will need to be manufactured and transported in order to heal or replace old and broken infrastructure. This would decrease the CO2 emissions produced by infrastructure maintenance. Again, these are estimates and much more research is necessary in order to accurately assess the environmental and economic impacts of SAP concrete. After analyzing the benefits and drawbacks of each concrete alternative, I have come to a conclusion about which should be implemented in construction. Both of these self-healing concrete methods show great promise and could be implemented in the construction industry in the near future. However, after comparing them to each other and to traditional concrete, I do not recommend that either self-healing concrete replace traditional concrete at this time. Bioconcrete is currently the better of the two options, but is much too expensive to be used in construction. It is currently double the price of Portland cement concrete. The price will need to drop significantly for construction companies to see its positives. Also, while there have been some positive tests completed showing bioconcrete's compressive strength, more testing is necessary before the construction industry will trust the results. Superabsorbent polymer concrete is currently the weaker option of the two, but shows more promise than bioconcrete. Unfortunately, it's simply too under-tested to be recommended for use. Despite their inability to be implemented in construction right now, these two concrete alternatives are cutting-edge technology that show great potential to help improve our world. Thank you.